I think at 13.1. Oh, first of all, let's see your comments. Let's see your comments first. Okay, so we'll definitely, I'll try to focus on some of those things. And the first part of your homework is to do what? I already gave you one homework assignment. Journal, homework, yeah, that's right. Journal, standard entry, how's life, how's math? So on 13.1, that's right, r to the n, that's right. Form, sure, x equals sine t, y equals sine t, and z is equal to root 2 cosine t. Now what'd you do?
I then realized that if you square both sides, x squared plus y squared.
Both sides? What sides of what?
Of the parametric.
Each parametric. X squared is equal to sine squared t. Y squared is equal to sine squared t. And z squared is equal to 2 cosine squared t.
And then if you add x plus y plus z.
Okay, so you do x squared plus y squared plus z squared is equal to sine squared, 2 sine squared plus 2 cosine squared t, which is equal to 2. So now you know that this follows x squared plus y squared plus z squared is equal to, so what is that? That's a sphere with radius? No. Close. Sphere with radius root 2, correct. Ah. So, can you sketch that? A sphere with radius root 2? Sure. So each of these is root 2. Like that. So there's your sphere with radius root 2. But what else do you have to mark on this thing?
Where the actual space curve is.
Where the actual space curve is. So the space curve is on this, right? Somewhere on there, but we don't know where it is. Okay, so how do you logic that out? So we know that that's very important right there. So if we draw the xy plane in here, x equals y where? It equals y, x equals y on this plane right here. That's slicing this. Correct? Do you see what I mean? X equals y. So both of these things has to be true. It has to, the space curve travels along that restriction, and it travels along, there's restriction number 1, and here's restriction number 2. So if we narrow down where this thing can be, yeah, it's with the intersection of that plane. So where is that? And I'm going to try to draw this the best I can. It's a circle, kind of goes like this. It goes back, and then down, and then up like this. Do you see it, everybody? It's diagonally cutting the sphere. Are we okay with that? Okay, so how do we figure out which way it's turning, though? So this is the path. This is definitely the path right here. It goes down like that and comes back up. So plot some points, essentially. Plot some points. How about time equals 0? What's sine of 0? 1, 1, and 0. Oh, sorry, sorry. What's sine of 0? So 0, 0, 1. So at time equals 0, it's right here. 0, 0, root 2, thank you. Keep on going back to unit circle land in my head. 0, 0, root 2, so that's right there. What about at time equals pi over 4, yeah. It's going to be root 2 over 2, root 2 over 2, and 1. 1, right? So where's that going to be? What octant would that be in?
We don't have a naming convention.
We don't, but the first one generally is said to be...
The first one.
Which one is the first one?
All positive.
All positive, exactly. So it's going to be right about here.
That means
right?
rotating.
So it's rotating like towards us at a diagonal. So here are the arrows right here. Draw, let's go with green. I don't know. Can't really see the green, but there you go. So it's circling like that. That one's a tricky one. So you have to, it's on this sphere, but where on this sphere? Keep on investigating. You know, x is equal to y, so it has to intersect the plane x equals y, and then you just plot some points to get the direction. That's how you do it. But the hardest part, I think by far, is the hardest part for me at least, is doing this. Like, squaring it and then noticing, look, it folds really nicely together. The reason I think that's particularly challenging is because there's no way for me to say always see. There's no mechanical system to check. You just kind of have to notice, sines and cosines, we want it to fold, a sphere. It's tricky. Okay, another one. do a little bit more than plotting points. We'd like to be a little more accurate in what we know. So let's look at the shadows that this space curve, this is a space curve, right? It's going off. So let's look at the shadows it makes on each of the planes. So on the xy plane, that's when z is 0. That's when z is 0. The xz plane is when y is 0. So how can we figure out what the shadows are? On this one specifically, how can we figure out what the shadows are? Parametrically, right? So what does x equal?
T squared.
X equals t squared, y equals
T to the 4th.
t to the 4th, and z is equal to
T to the 6th.
t to the 6th. We know what each of those look like independently, right?
Or not.
Yeah, well, watch this. This is something I want to show you today. Let's try this here. Hold on a sec. It's called a FOLEM, it looks like. It's an implicitly defined function. Finding slopes of tangent lines involved taking the derivatives implicitly. Look what it does for you. There's the input, there's the alternate. Oh, it looks like this. It gives you alternate forms. It gives you the roots, it gives you solutions, and it gives you the implicit, and it simplifies it for you. So that's pretty neat. It's actually doing algebra. This is a great thing to use. Check answers. It's a great thing to. It's bold, exactly, yeah, which is kind of a terrible notation if you ask me. T times A cross B, and this turns into, yeah. Let's see if you understand this. T squared A cross C. Does everybody see why that's true? Anybody see it? There's a T floating in front of C, and there's a T floating in front of A. You can kind of distribute. Those are the rules. Some of the rules from cross products. So if you take the derivative of this, r prime of t. Anybody want to guess what the derivative is? T is a constant, correct? Right? What's the derivative of 6x?
A cross B.
6.
That'll be A cross
So what's it going to be? A cross B plus what?
2T.
2t A cross C. Yeah. Once you pull the constants out to the front, you look at what's in front of it. Yeah, that's it.
Well,
That's totally
why
it.
is T a constant?
Because it's a count, because it is. The derivative is continuous. I think it tells you that in the book. Does it tell you that? Smooth equals continuous derivative. So why? Okay, how many people understand what smooth is?
There's no cos.
Yeah. Did anybody actually look up in the book where it talks about smooth? No, no one did.
I think it talked about it in 2D.
Well, what are we saying for smooth here? We're saying that the derivative is what? Is the derivative continuous?
Yeah.
So remember, curve, 3 space, it's smooth if each component is continuous and the derivative is not equal to the 0 vector on the interval you're looking at.
Oh wait. Is
Except
it
on the
also
endpoints.
in 3-bit space?
For the 0 part, yes. In two,
But the third one is 2-dimensional.
the third one is 2-dimensional. Let's just say, I guess they're adding this in for vector functions. For vector functions. The definition for smooth, they're just adding that in. Arc length. Arc length. Arc length, arc length. Have you talked about arc length before?
Yeah.
Yeah, you all took BC calculus, right? So did you have to learn about arc length?
Pythagorean.
Lots of Pythagorean theorem, lots of Pythagorean. You're trying to find all these distances, right? And if I calculate the distance from here to here and add it to there, is that going to be the exact length of that curve? No, but if we take a limit and break it up into a little tiny pieces, what does it approach? The actual length of the curve that we're looking at. The actual length of the curve we're looking at. So the limit that we're actually looking at, is this. And you've seen this before. Hopefully you've seen this before. So it's the limit as n goes to infinity, so we're making an infinite number of cuts. And this just means the distance from pi minus 1 to pi, so any 2 consecutive points. And how many of you have seen this right here? If f prime is continuous on the closed interval a to b, then the length of the curve, don't move, of y equals f of x is the integral from a to b of the square root of 1. Do you remember this? Does this ring any bells? Kinda. It's there. It's there in your head somewhere. It's there in your head somewhere. So it's just dy dx squared. So you find the derivative, you square it, you add 1, and you integrate. Do you have some some experience with this? Unless you have very specific functions, is this an easy thing to integrate? No. If I could give you just about anything, and it's going to be, like, for example, unless it's a very specific thing, are you going to be able to integrate it by hand? If I put a round and 1 plus blah, 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 blah. Do you have many ways to integrate that by hand? No. Unless it's some inverse trig function, are you kind of SOL? Yeah, you kind of are. So, you're going to use your calculator a whole lot.